questions on the homework? Oh, by the way, so Monday we have gateway test. Now there is one variation on the gateway for how we did it last time. Okay, it's still you have to get 8 out of 10. You get 8 out of 10 the first time, 30 out of 30 in the grade book. Then you get 2 attempts within the next 3 or 4 days to get to get 8 out of 10. If you do, you get 27 out of 30. Then you get a couple more attempts within the next 3 or 4 days, and then that's 24 out of 30, and it keeps going like that. So it's based on how many attempts you take, but it's also that time period. If you wait a week and don't try your second attempt, and then you come in and pass it, it's already down to 24 out of 30 because you waited too long, okay, in there. So you got to be coming in and doing that. Now, I had started to do a thing. We had talked about how, well, at some point you could take the best grade you had. So if you had a 5 out of 10, well, you could just take 50%, 15 out of 30 is your grade. Well, that's not going to be an option anymore, okay? You've got to get 8 out of 10, or in the grade book it goes 0 out of 30, okay? Because what happened was people were just trying once and then not even coming in and not even doing it, okay? And that's not going to be an option unless you want a 0 out of 30, okay? Now, if you come in and taken it 5 times, 6 times, 7 times, and you're not passing it, then maybe we can negotiate some sort of a situation, okay? But if you're going to just not even try and then just not even come in and take it, then you deserve it, okay? So that's what it's going to be, all right? So that little change, but otherwise everything is basically the same way we did it before. So this week is all going to be about practicing, getting ready for that. But just like last time, when we get to next week, we're moving on, right? We're moving on to other stuff. But if you haven't passed it, you're going to have to be staying on top of that and coming in and getting that taken. Okay, so now questions on the home. When do you want to take a look? Number 7. Okay, read me number 7. Hang on here. Let me get rid of some stuff here. Hey, look at that. Rebound. Number 5 on the season and number 8 in the career. She is number 1. E to the what? E to the 1 over x over x squared dx. Now, the nice thing about today's homework, which will never happen again in any more homework the rest of the week, is they told you what to use for u, or they gave you hints as to what to use for u. In this case, they told you to let u equal 1 over x. Now, let's learn from what they told us, and let's talk about why you pick certain u values for what you want to do. Now, yesterday I told you you always would look where? The inside. Now, as you noticed when you went through the homework, that there's somewhere it's not on the inside. You're not letting u be the inside. But the first place you would think about is the inside of a function. So inside the e, we have 1 over x. Now, the other thing that you might have noticed, well, you tell me, did you notice a different situation that they let u be sometimes? Mm-hmm. What was it? Yeah, what did they let u equal there? Just a part of something, there, right? So, and the one I was thinking of was the denominator. Did you notice somewhere they just let u be the bottom? 13. Was that 13? Where they just let u be the, and so there are various things that will work to let u be the bottom, but here's what really determines what you want to be the bottom, is our next step. What do you do after you write what u is? The derivative. And now, yesterday, Josh was gone, when we do the derivative, du over dx, right? Now, this would be x to the negative 1. So we do the derivative, that would be negative 1 x to the negative 2 dx. Now, because of that dx, what we really were doing there, Josh, is we said we're going to pick our u, and then we're going to do the derivative of that with respect to x, and then we're going to take this dx and we're going to multiply it over to this side here. So that's why we write it like this, and I just skip that step for now, and I just do that. Okay? Now, but here's the reason. Here's what you want to be looking for as you start to get better at these. what you're doing is you're thinking a step ahead, and you're saying to yourself, you know what, if I let u be 1 over x, which is x to the negative 1, my du is going to be x to the negative 2, which is really a 1 over x squared, which is this right here. And that's what I'm looking for. So the thought process is, okay, if I pick this for u, the du will be this, and that is setting right there in my integral. That's what I'm looking for. All right, so when we substitute this into a new integral, this would be e to the u, and this stuff, except for the negative 1 that I would move over to the other side, this would be, this 1 over x squared dx would be a negative with a du right there. And so now the antiderivative, now here's where that page 333 comes in. The integral of e to the u du would be just e to the u plus c. So now we've got the negative e to the u plus c, and then we put our u back in, so it's negative e to the 1 over x plus c. Let me see. Okay, so there's our final answer. So, Allie, what was the question, really? I mean, we did the problem. Oh, yeah, negative, just like any old number where we talked about we could just kind of divide that over to the other side. Now, we do have to concern ourselves a little bit about how we move stuff around. That we ran into one in the other class that I'll talk about here in a little later. But yeah, dividing stuff over a negative, we can move that back and forth here in our substitution. That's just fine. Okay, another one. Number 10. 10's a good one because 10 shows a technique that we have to use quite a bit. Okay, is this the problem on 10? Okay, and again, they help us out because they tell you to let u equal x plus 1. Right? Now, that is one of our strategies. One of our strategies is going to be let u be the inside, but another one is because there's not really an inside here. So another thing we do is we let u be the bottom. Now, why in the world would we let u be the bottom? Well, you'll see what's going to happen here. So we go ahead and let u equal x plus 1. So what's the du? Just 1 dx. So I usually don't even write the 1. I'll just write dx, right? 1, because it's really times. I mean, so it's 1, and then you times by dx, so it's just dx. Now, here's where showing your work. Now, I noticed some of you guys, I'm going around there and looking at some of them are odd, whatever. I'm looking at some of these, you just got answers. Now, is it possible that you can just think backwards and get the right answer on some of these? It is possible, yes. And on the gateway test, if you're able to do that, right, you know, that's okay. I'm not going to grade it based on did you show your u or did you show those things. If you've got the right antiderivative down there, you know, perfect, I mean, it's got to be right, then you're good. Now, one nice thing about the antiderivative gateway test is there's not nearly the algebra simplifying. Remember that was kind of a big deal on the last one? You did your derivative, then you had to combine some things and cancel maybe and look for that kind of stuff. That's not really true on antiderivatives. Antiderivatives are pretty much, you rearrange them, you get them so they look like page 333, you do your antiderivative, you put your x's back in for your u's, and you're pretty much done. Okay, so that's a good thing here. All right, so now I'm ready to substitute. Well, obviously this would be what? X plus 1. Jacob Rolla, what would I put for this x plus 1 right here? That's just a u, right? And I got du equals dx. So that means this right here could be taken out, and a du can be put in its place. This is where, a problem like this is where I like to do the circling. Because now it's glaring, it's very glaring to me that I've got this extra x sitting there. Right? I got this extra x that I haven't subbed out yet. Well, what does x equal? Yeah, right here. This is perfectly legal to do. I can subtract a 1 from each side. Now, I would never do a subtraction on this side, you know, and I'll show you one later, because this has got multiplication in it, because that dx is like multiplied, so you couldn't subtract, and you'll see what I mean by that. But on this other one, here, we can take this and we can solve that right there. So now I can take the x out and I can replace it with a u minus 1. Now, you might be looking at that and saying, well, gosh, that didn't really do anything. It looks pretty much like what we started with. How did that help? We can split it apart. And this is why letting u be the bottom is a good thing, because we cannot split a denominator, right? I mean, you go back to what you know about fractions. Think about this. If I had 3 over 4 plus 6, I know that that is equal to 3/10, correct? Well, you cannot split that denominator like this. 3/4 plus 3/6 would not equal 3/10, okay? That is no good. However, if it's the other way around, 4 plus 6 over 3, I know that that's 10/3. I can split that into 4/3 plus 6/3, right? So I can split a numerator over a single denominator, but I cannot do it the other way around. So by letting u be the bottom, you've turned the bottom into a single thing, and having a single denominator is helpful because it may allow us to split it apart, and that's what we're going to do. So we're going to do u over u, which is 1 over u. Now normally I would write that as a negative power. This is going to be an ln. If this would have been 1 over u squared, then I would have written that as u to the negative 2 and done my power rule. But I know 1 over u to the first is an ln, so I'm going to leave it like that. And then I've got my du. Now notice I haven't done the antiderivative yet, so I just leave it. Now I had a group working in the math office yesterday, 4th block, and they came up with this one and they finished it, and they looked in the answer book and it was different. And that might be why some of you asked about this one, but let's keep going. What's the antiderivative of 1? Not x, right? We're doing it with respect to u. It's u. Okay, antiderivative of 1 over u? ln u with bars around it, plus c. Now, finally, we go back to our x's. So in place of u, we put x plus 1. This was 1 plus x, actually, in the original problem. X plus 1, 1 plus x. Okay, and then ln x plus 1 plus c. Now, if you stop right there, that would be acceptable. However, if you look it up in the back, what did you notice? Anybody look it up in the back? Yeah, they did not have a plus 1. And actually, somebody in their class tried on their calculator and the same thing. It does not put the plus 1 in there. Well, the plus 1 just adds to the c to become just c. It's kind of weird, but it just kind of gets absorbed into the c because you have 1 plus a constant, which is just another constant. So I don't care if you do that. Typically, like the calculator does, the back of the book will do that. So they don't have the plus 1 on there. They just have x minus ln x plus 1 plus c. Okay, either way is fine with me. All right? Good stuff. What else? 13. 13 says what? The integral from
0 to 3.
2x squared okay, dx, and then they say that that equals, now I'm going to put a box here, boxes where they have an a and a b, right? And then what do they have? A 1/4 u to the negative 3 du. Okay, so what we're supposed to do here, basically this is one more step in your evolution here. In the first 10 problems, they told you what u was. In this one, they're showing you what you would end up with if you pick a certain u. What your job was is to figure out what must they have let u equal here. I think they let u be the bottom inside of the bottom, right? Now remember, we just got to talk about how you let u be the bottom, but our first thing we learned was let u be the inside. And so if you have a bottom with a power, you're better off just letting u be the inside of that, not the whole bottom. Okay? If you've got like a square root on the bottom, or a power, a bunch of stuff raised to a power on the bottom, you're better off letting u be just the inside part. Okay, and you'll notice, because what's going to happen is, when you practice enough of these, you start going down the wrong road and you get stuck. And then pretty soon you do that enough times, you start figuring out, oh, I don't want to go down that road. I remember last time I tried that, it got to be a mess. And so you figure out what to do. All right, so we get 2x squared plus 1. So the du is what? 4x dx. Now, again, what would my thought process have been? Remember, after we get done with this problem, the rest of the time, we're not going to pick the u for you. You're going to have to figure it out. So if I didn't have any of this, I'd be looking at this and I'd be saying to myself, hey, if I let u be the inside, I'm going to get 2x squared plus 1. So the du is going to be 4x dx. I don't really care about the 4 because I can divide that over. But I'm going to have x dx. And sure enough, right here is an x dx sitting there. So I know that's going to be a good thing. So that's the thought process when you pick your u. All right, so again, the 4 I'm going to move over here as a 1/4. I got my x dx. So some nice things are happening. So I'm going to just kind of ignore this here, and I'm just going to pretend I was doing it from scratch. So I'm going to look at this. I'm going to say, sure enough, that's going to be a u cubed on the bottom. And the rest of this, the x dx, that gets subbed out right there. So that's a 1/4, and that's a du, and that's a 1. So sure enough, 1 over u cubed, that would be u to the negative 3. Now let's fill in the a and the b. So this is the very last problem I did yesterday in class. Notice we haven't subbed out everything. We didn't sub out these. Right? We didn't sub out these right here. Now what kind of values are these? Those are x values. Right? This is the area from 0 to 3. If you look at a graph, you got an x and a y axis. The 0 and 3 are on the x axis. They are the area underneath there. So these are x values. Since we took out all the other x values, we should take those out as well. Now you don't have to. I talked about how you could turn this back into x's and then use the 0 and 3, and that's fine. But we should know how to do it. So if this is an x value, I could plug that right there for that x. And what do you get? You get 1. So that means the u value for that x value would be 1. And if u is a 3, excuse me, x is a 3, we get 18 plus 1, we get 19. So the a and the b would be 19. And the nice thing about this, and then this would just be u to the negative 3, so now I can do my antiderivative. So I raise that up to a negative 2. I still have the 1/4 out here. Divide by negative 2, which would be that. And I'd have u to the negative 2. And I don't need the plus c, remember, we got right bracket. So I got 1 and 19. So this would be negative 1/8. Actually, I would probably do it like this. I would put the u squared down here, right, the negative 2. And then I would right bracket that from 1 to 19. And then we would just put in negative 1 over 8 times 19 squared minus negative 1 over 8 times 1 squared. And then simplify that out, whatever it comes out to be. Right? Give them some big numbers. Okay? But that's what that one's going to look like. Okay? So they had just, what they were trying to do there was just do part of it for you and let you kind of figure out, okay, what do I pick for the u? What did they pick for the u to make that happen? All right. What else? Let's save that one and I'll talk to you about that one. Because I want to give you guys a bunch of work time today and so allow you to answer. So what was your question about 11? Because it's really just like 13. No, that's okay. Well, you know what? Okay. That is a pretty good one, actually. Tell me what the original was. Yeah, this is worth talking about because, okay, forget what they had over there. Let's talk about this one as if we were doing this one from scratch. Okay, So we're gonna try to figure out what let u equal. So far I've told you what about what to let u equal. Inside. Is there an inside here? Not really, not that jumps out at you anyway. And the bottom. Okay, so let's say that you said, all right, I'm gonna let you be the bottom. So let's think ahead here. So if I let u be the bottom, 1 plus x to the 4th, what's the du? 4x to the 3rd dx. Is there an x to the 3rd dx setting? No, there's only an x dx setting there. So that is what would dissuade me from using the bottom as my u. Now, if I change this integral just slightly and make that an x cubed, then that's what I would have wanted to pick. If this would, because I could give you that one, right? We easily could have had an x cubed up here. Then I would have let u be the bottom. That would have been the way to go. But it's not. So then we start thinking, well, what would be a good u that when I did the du would give me this x? An x squared would have been nice. Well, let's see. What would that have done if u is equal to x squared? Well, what do I got right here? Yeah, this is x squared squared, right? So this would be like 1 plus u squared, and oh, what is that? What is a 1 plus u squared on the bottom? That's arctangent. Okay, so that's another little thing you're going to, as you work more of these problems, you'll start to recognize. When you see a 1 plus u squared on the bottom, or a 1 plus something squared on the bottom, arctangent should come to mind. That's not always going to be that, but that should come to mind as something to try. If you have a square root and 1 minus something squared, arcsine should come to mind. All right, so that is why they chose x squared as what to use. Because now the du would be 2x dx. We can see that I don't have a 2 anywhere there, so I'm going to move that over by dividing it. And I get x dx. And so when I go to sum things out, sure enough, this bottom is going to be 1 plus u squared. The dx and the x, I can see right here, is equal to a 1/2 and a du. There'll be a 1 there on top. And sure enough, I've subbed everything out. Okay, now what I haven't subbed out are these numbers, so let's do that. What would -2 as an x be? Squared, that would be, u would be a 4, so that would turn to a 4. Take this 1, plug it in for x. That would be 1. And so now what I see is I've got an arctangent there. So I've got 1/2 arctangent of u from 4 to 1. I leave off the plus c, right? And I do my right bracket. These are now u values because I substituted these x values in for x, turned them into u's, and so now I can plug those in. So I got 1/2 arctan 1 minus 1/2 arctan 4. Now arctan 4 is not something I know, but arctan 1 is something I should know. What's arctan of 1? No, it's the angle whose tangent is 1. What angle has tangent of 1? Pi over 4. Pi over 4. Now, we need to know that. If you run into one of these with an arcsine or an arctangent, now arctan 4 is not one we would know. But what you're looking for in an arctan or an arcsine, you're looking for 1/2, square root of 3 over 2, root 2 over 2, or 1 or 0. Those are your special angle values for arcsine and arctangent. So you run into like pi 6 or pi 3rd. So if we get into one of those, right, so this would be pi 8s here, minus 1/2 arctangent 4. Now I'm not saying that's going to happen very often, but if it did on the gateway test, you'd want to be able to do that. So you'd have to think about that. I think so. I think so. I don't know that it's going to happen, but put it this way, there wouldn't be more than one, right? Wouldn't be more than one. So you can still, if you mess it up, you can still get by with that. But so I was saying earlier, there's not nearly the kind of simplifying that there is with derivatives in this thing. But when you're doing a definite integral, we want to simplify those numbers down as best we can. Okay? All right. What else? How about in that section on the indefinite intervals. Oh, let me make a comment on 22. On 22. They said that what 22 was about, it basically had to do with trig, and because of trig identities, you can make different substitutions. And what they did with that one, they had the integral of secant squared times, what was it? Secant squared times tangent x. Now, it's kind of a cool deal, because what they were saying, if you let u equal tangent, then what's the du? Secant squared, and somebody was mentioning to me this morning that it's kind of strange when you're doing these antiderivative problems that when you do the du step, you're doing the derivative. So right within the same problem, you've got to be remembering your derivative rules and doing your antiderivative, so you can't get them confused, right? So you got to make sure you do that. But if you let u be the tangent, then the du is sitting right there. But the other thing you could do is, like they say, is you could let u be secant x. What's the derivative of secant? Secant tangent. And that's also sitting there. So if you let u just be one of the secants, you have a secant and a tangent left, it's also sitting there. Now that doesn't happen very often. Rarely do you have multiple choices of what you can pick for the u. Usually it's just pretty much one thing that'll work for the u, and that's it. But every once in a while you do have some options, and it still should come out the same. So their point was, depending on which one of those you do, on one of them you get 1/2 secant squared x plus c, and on the other one you get 1/2 tangent squared x plus c. How come those are the same thing? If you graph them, it's the same graph. That's true. Here's the real reason. It's related to what we were just saying a little bit ago. There is a trig thing that's this, which also means that secant squared minus 1 is the same as tangent squared. Well, why are those two equal? The minus 1 or the plus 1 would just get absorbed into the c. So technically, tangent squared and secant squared are not equal. Tangent squared plus 1 is secant squared, but when you're tacking on the plus c, the plus 1 and the minus 1 doesn't matter. So that's the whole point of what number 22 is about. Okay? All right, not something that's really going to be an issue for the gateway test. All right, anybody have another one on one of the later problems down there? We've covered several good things, good situations that we have to be aware of. The splitting apart the integral, stuff like that. Another algebra thing, there's two main algebra things that come up in these problems. I might as well just tell you about it right now. One of them we've just discovered. You know, we had x over x plus 1, which we cannot do anything to algebraically. When we switched it, when we did our u substitution, we ended up with this, which is a good thing, right? Because now we can split that apart. Here's another thing that you're going to run into in some of these problems. You're going to have a problem similar to something like this, where you start with this. Now, unfortunately, we can't do those separately because they're timed, so we can't do the antiderivative separately. So we would probably let the u be what? The inside, the 2x plus 3. Now, what will happen is you will turn this into another integral. What will happen is, since you let u be the 2x plus 3, you'll end up with u to the 4th, and then the x will get replaced by, I don't know, something, I'm just making this up, but you know, maybe it ends up being something like that. Now you look at this and you look at that and you think, what advantage have I gained here? What can I do with this that I couldn't do with this? Distribute. You cannot distribute an x through this power. But by letting u be the inside, we've turned our power into a single thing, and then we've got this without a power on it, and now I can distribute, and then I would be able to do my power rule thing on that. So when you get into some of your homework today, this is the kind of thing that's going to happen. You're going to let u equal this, but then you're going to have this extra x setting there. Well, we saw how you can then solve for x. You can then substitute that in for that x, and then you're going to have a situation where you now can do some algebra where before you couldn't. So those are a couple of the algebra things that happen that you need to be aware of and that you want to work with. All right, let me show you a couple of things here, and maybe give you a couple to try, and then we'll let you work for a while here today. So on our class website here, on our Google website where I have the videos and so forth. All right, if you come down the left-hand side here where it says web links. Now, we're not going to really spend much time on this yet, but later in the week, this will be a good place to go for some extra practice. There's a link that says antiderivative practice. Now, down in here, here it says there's a good review with some antiderivatives, but when I click on that, that seems to be gone. So that one's no good anymore. Tomorrow, a minute here. Let's try this again. All right. Tomorrow we'll be doing some stuff, something called integration by parts. So here's a link to some integration by parts. Down here it talks about the inverse trig functions. So I don't know, I haven't been to that one, so I'm going to hold off on that. Right here it says you can find lots of practice for using substitution by taking this quiz. So let's go to this. So elementary integrals, so those would be your basic antiderivatives, and some integration using substitution. So we click here, start the quiz. Okay, and here's a problem right here. All right, so go ahead. What do you suppose you're going to do with this one? Split it up. Okay, go ahead and try this one. Go ahead and try this one, and we'll check our answer. So just on your homework paper there will be fine. It's 3x cubed minus square root of x plus 6, and then all over 2x. All right, what do you get? D. Okay. I believe that is correct. Now, think about what would happen if you split it up. You'd subtract the powers. I really like fractions, not division. I don't think you should put 3x squared over 2. I think that's confusing, and it'll confuse you with quotient rule or variance, whatever. I think, so this should be 3/2 x squared. This would be the 2 on the bottom, so that's 1/2. This is x to the half over x, so you would subtract those powers. 1/2 minus 1 is -1/2. And then here you'd have 6 over 2, which is 3. I would leave the x on the bottom. I would not make that x to the -1 because it's an ln. When you have x to the first on the bottom, then it's just going to be an ln. So I would leave that as 3 over x. Now, we're going to do our power rule. So we raise that up 3. We divide by 3. Well, that's going to cancel those 3's. We're going to raise that up 1, which is 1/2. And divide by 1/2. Well, if you divide by 1/2, that'll cancel that half. And then this is just going to be, the 3 doesn't change anything, right? 3 over x is the same as 3 times 1 over x, right? So that's 3 ln x. Do you notice that they didn't have natural logs on the, or they didn't have absolute value bars on the log? Did you notice that? Hopefully you did when you wrote it. Well, or hopefully you knew why you didn't need them. But here's what it ends up being then. 1/2, so the 3's would cancel, say 1/2 x cubed. So you look at this, you got minus square root of x, and then plus 3 ln x plus c. Now, it's always okay, well, it's not always, but in these problems, I think it's okay to have the bars, even if they're not necessary. Why did they leave the bars off? Did they make a mistake? In the original problem, there was a square root of x, which tells us the domain of this problem, x has to be positive, cannot be negative, or this would be no good. So since x has to be positive, there is no need to put bars around that because that's what the bars are there for, to make that be positive. But we already know it is, so you can leave them off. That happens from time to time in ln problems, so it's good to know that and leave them off if they're not needed. But if you're unsure, put them in, will be okay. All right, so that is that website. Let's put D, check our answer. They say you're right. They go through and they kind of show you some of the steps and whatnot. So there's a bunch of those. Now that wasn't a U substitution one. It says get the next one. Okay, now this one, it's hard to see. It's x, and then it's e to the 6x squared. What do you suppose for your u? Just the 6x squared, right? Let u be the inside, 6x squared. Because what's the du? 12x dx. I don't care about the 12. We'll deal with that. But there's an x dx in my du. And right there is an x dx that will sub out quite nicely. And so things are going to work nice. So that 12 would divide over. We'd end up with the 1/12. I don't think it's that one, though. I think it would end up being that one, right? There shouldn't be an x in there, because what you'll get is you'll get e to the u. You'll have a 1/12 out there, right? This is what I was saying by when I said that it's possible after you've practiced some of these. I see some of you with these answers just with no work. You know, it's possible when you get good enough at these, I could look at this and say, well, I have 12x dx. The 12 will divide over. That's 1/12. My x dx will go away. I'll have e to the u. Antiderivative of that is e to the u. Put the 6x squared back in. I'll have e to the 6x squared with the 1/12 out there. It's got to be d. So yeah, could you maybe, as you get better at these, do that without showing a lot of work? It's possible. Okay. I don't know if it's smart, but it's possible. All right. So that's something on the website there. Let me throw another one at you here out of the book, because that's going to be part of our homework. Is just some more book problems, and I got a new packet for you with some more problems. We're just going to practice, practice, practice. Here's one I wanted to throw at you. This is number 49 in the book. Make sure I get this right. All right, try that one. Talk it over with a partner if you want, or if you think you got you think you know what to do, go ahead and go at it. All right, before anybody gets too far down the wrong road, I know you might not have time to finish it. That's fine. Go ahead and keep working, but we'll see if you're headed the right way anyway. What do you think for you? One thought is x plus 1. Anybody think about the whole bottom? Tried that and you got something bad. Okay, now, and listen, those are both things we've talked about. We talked about letting U be the whole bottom. Somebody in the air class even said, how about foiling this out first, which actually works the same as if you don't foil it out first. But if you let U be the whole bottom, so let me show you what I got. So if you let U be the whole bottom, so U would be the whole bottom. So then your next thought is, what would the DU be, right? So the DU would be bring down the 2. You'd have x plus 1 to the first, times 1, derivative inside. So it's basically 2x plus 2 dx, right? So, and then I would ask, is that sitting there? No. Almost. And it's too bad. If this problem would have been a 2 right here, just change it that little bit. If that would have been a 2, then this would have been a great idea, right? Because 2x plus 2 dx is saying right there. Now, somebody in their class said, well, what about split it apart? You do have a 2x dx sitting there. I said, but you don't have a 2x dx here. And they said, well, subtract 2. Can't. Right. When we were doing that problem a minute ago, up here, with the u, we subtracted. But you cannot subtract, because remember where this came from. This was du over dx equals 2x plus 2. And we multiply that dx over there. It's like that's, right? We can't just take that plus 2 out of there and subtract that over. Plus, that would give you du minus 2. And we don't want that. We don't want a du minus 2. The du's got to be by itself or maybe multiplied, like a 1/2 du. We can do that. But we can't do a minus, so it would be bad. Now, later I'm going to show you a little trick where we could have done some splitting apart and get fancy, because some problems, we could write this as 2x plus 2 plus 1. Wouldn't that be the same thing? And then I could split this, but then even that is going to get me into trouble. When I split it, I'm going to run into something I can't really do very well. But anyway, so I can keep that together, keep that. The best bet, really, is to let U just be the inside. And again, I think earlier I said something about that. I said if you've got a power on the bottom with an inside thing, a lot of times it's better to let U be just the inside. So let's see where that leads us. So if I let U be just the x plus 1, then the du would just be 1 dx, or just dx. When I start subbing out, that would come out and be that, right? And I went ahead, excuse me, it's a u squared on the bottom, so that's going to be u to the negative 2, okay? And then the dx is just going to be the du, so that takes care of that. So the problem is I've still got this 2x plus 3 up here. So then what I do is what we did earlier. I'm going to subtract a 1. So x is going to be u minus 1. That's legal to do there. The subtraction's okay there. And now I'm going to put u minus 1 right in here. So I'm going to have 2 times u minus 1. And I know some of you were headed this way. I just didn't give you enough time. But I'm going to let you work here. So we would put a u minus 1 in for the x. So we'd have 2u minus 2 plus 3. So 2u minus 2 plus 3 would be 2u plus 1. And then I'm going to stick that right over here. And that would go in place of the 2x plus 3. 2 times x plus 3 simplifies down to that. Now, I warned you about this, or not warned you, but I showed you this algebraically a little bit ago. What advantage is this of what we have here now? We can now distribute. So we're now going to have 2u to the negative 1. Oh, that's going to be an ln. And then we're going to have plus u to the negative 2. Right? So this is actually going to be a 2 over u. So that's going to be 2 ln u. And then raise that to a negative 1, divide by negative 1. So we're going to have u to the negative 1 plus c. And then finish it by putting your x's back in. Okay? And there you go. So, a lot of work to go through to get these antiderivatives, but that's the way it is. I mean, antiderivatives, they're just not it's just different than derivatives. It's because we're working them backwards, and so it just doesn't work the same way. It's not like we have a rule. If it looks like this, you do this. We're trying to work with it to see how we can get it to go backwards into an antiderivative, and so these are the things we have to do. All right? Okay, so here's your homework for tomorrow, and I'm going to let you have the last half hour here or more to work on this. The boldface there where it says page 340, do some of those. I would say at least 8. Let's do at least 8. Just pick any 8 out of that section there on page 340. That's in your book. We're in, that's the section we're in, yeah. Page 340 is in 5.4. Right? And then this is another little LH packet. This is another set of exercises. Now, you notice here on this row, we've got these different pages in the LH packet. Now, I'll tell you in a minute which ones I want you to do. Right now, it's 8 out of this page in your book, okay, page 340. So 8 of those, pick any 8. Now, you see these different pages. Well, here's the LH book was organized by function. So you would have, when you learn the antiderivatives in that book, you would learn them using algebra type functions, and then you would go into the trig functions, and that was in another section. That's why there's another page. And then you would go into the e to the x and the log functions, and that was in another page. And so that's kind of how these are broke up. So what I want you to do is this line right here, and then 8 on this page. Okay? So this is the first page of that little packet that I just handed you. Okay? And that's about 9 problems, and then 8 problems out of there. Okay, and you certainly can do more than 8, but I think 8 would be the minimum to practice. And then we're going to learn integration by parts tomorrow and see that and then review. And the last couple days this week are a lot of review and even some in-class review time. All right, so the rest of the time is yours for work.